you very much. And congratulations to Michelle for your birthday. I'm not sure whether there's a word for 62nd birthday. So the work I'm talking about is joint with Gwyn Bellamy, Thierry Lavoisier, and Tom Nevins. And tragically, while we were finishing this off, Tom died. So sort of a memorial for him. So we can view this work in two ways. I mean, the first way, more abstractly, is that we're always interested in differential operators on a vector space endowed with the action of a reductive algebraic group. And this is closely related then to a certain Cherednik algebra. And that interrelationship enables you to get strong results on structures of various important D modules, G-equivariant G modules, or for modules over the Cherednik algebra. I actually want to take a somewhat different view, a more concrete view, where I'm interested in taking just one module, or one class of modules, and looking at them in great detail. And in the process, we'll generalize some classical results of Harish-Chandra using these ideas. So to set that in motion, I'm going to first think about these results of Harish-Chandra. So that's handy. Situation I've always got a reductive complex Lie algebra G, adjoint group capital G, Cartan algebra H, Weil group W. So the usual notation. So then the adjoint action of G on little g, and I'm going to call it, when I think about G as a representation, I'm going to call it V. You'll see why later. So that gives me actions on the functions on V, the symmetric algebra on V, and then on the ring of differential operators. And I can give you the action by saying that I've just identified D of V with the tensor product of C of V and sim V, where the second term we identify in turn with the constant coefficient differential operators. So that gives us various other pieces of notation. First of all, if I differentiate the action of the group, I get an action of the Lie algebra, and I can think of that as a map from the Lie algebra G to derivations on V, sitting inside D of V. And then I have the regular semi-simple elements. So that's just the space where the discriminant is non-zero. So in this situation, I'm just thinking of that as the coordinate function of the product of reflecting hyperplanes in H. So that's going to be my basic notation. And hopefully we can remember that as we go through. So turning to Harish-Chandra's theory, the modules he was concerned with, and we're concerned with, are the following. So the first one, I can take D of V, and I factor out both the image of the Lie algebra, so these derivations, and then the sim VG, a positive part of that. So these are constant coefficient differential operators. So most of the time I'm going to be talking about that module, but more generally what I will say will have analogues for a whole class of modules where rather than taking sim VG, I take the positive part of that, I take a maximal ideal in sim VG corresponding to lambda in H star. So here I'm going to use the Chevalier isomorphism, symmetric functions on V, which are G invariant, the same as symmetric functions on H, which are W invariant. And then in here, I take the maximal ideal corresponding to lambda in H star, or its orbit, W orbit. So that was not what he was really interested in. He was interested in G-equivariant eigendistributions on V0, where V0 is now a real form of V, and G0 is a real form of G. So what are these? Well, I can define them by a lemma by saying that's just the union of the homomorphisms over D of V from my G lambdas to distributions on V0. So why is that a reasonable definition? Well, there are two parts to it. First of all, G-equivariance. So being invariant for the group is the same as being invariant for the Lie algebra. So that would just mean that my distribution should be killed by mu of G. So that's why that's there. Secondly, it should be an eigendistribution, an eigenvector. Well, if you unravel what it means for m lambda to annihilate my distribution, you'll see that that actually means you've got an eigenvector corresponding to an eigenvalue lambda. So at least this definition looks reasonable. And this theorem of Harish-Chandra in this notation goes back to 1965, and it simply states that this G lambda has no non-zero factor module, which is torsion for the action of delta, the discriminant. And that in turn says that my eigendistribution cannot be supported on the singular place. Remember V0 prime, that's the regular part, that's where discriminant is non-zero. It can't be supported on this factor, on the difference. And that's pretty obvious, because if it's supported here, it's going to have to be killed by a power of delta, and that's not allowed. So again, this is still looking rather abstract. It's not, and again, why would Harish-Chandra be interested in these things? So he's interested in the structure of eigendistributions. And this allows him to get strong results about the structure of omega, or the structure of these eigendistributions. And the reason is because this result allows you to reduce questions about omega to questions about distributions on the regular semi-simple points. And their things are much better controlled. And in particular, this theorem 1 is the main part of the proof of his regularity theorem, which says the following. It has 3 parts. So we take one of these invariant eigendistributions, we restrict to the regular semi-simple part, then that's an analytic function. So we're told that analytically that's not such a hard theorem to prove. And the key point of theorem 1 is that that uniquely determines T. And once you know that, you can actually prove that T is a nice distribution. It's a what's so-called locally summable function. And then this was extended further to his distributions on the group G0, and ultimately applies Harish-Chandra's main regularity theorem for characters of unitary representations of G0. And the theorem he has there is, again, basically the same thing. Take this theorem 2 and just rephrase it in terms of characters of representations. So that's the theorem of Harish-Chandra that we're interested in, although we're really interested in the form of theorem 1, that we have a structure theorem for this G lambda. Second theorem I want to talk about for G lambda is work of Hotta and Kashiwara. This again can be simply stated. It's just that G lambda is a semi-simple D of V module with specified irreducible components. I might remark here that it's obvious, it's not hard to prove that G lambda is a holonomic module, so it certainly has finite length. And the key thing is then it's semi-simple. I might also remark at this point that the title of the paper comes from work of Hotta and Kashiwara. They introduced this name of invariant holonomic systems. And the reason for that is if we go back to the G lambda itself, really we can view this in 3 different ways. First of all, we've got the module, or we can take the corresponding eigendistributions, or we can just take this left ideal I thought of as a system of differential operators. And that is the invariant holonomic system of differential operators. Holonomic because, of course, we've got a holonomic module. And so that's part and parcel of this theorem of Hotta and Kashiwara. And they were interested in this result because, again, it gives you some deep consequences for the geometric theory of G representations and also for Springer theory of Weyl group representations. So again, it has a lot of applications. So then the third result I want to talk about in terms of these G lambdas at this level is results of Wallach and ideas of Wallach. So again, we have the Chevalier isomorphism, which appeared a bit earlier. We now think of as saying that the G-equivariant functions on V are the same as the G-invariant functions on V are the same as W-invariant functions on H, the Cartan subalgebra. So I can view that as giving us a homomorphism, sometimes called quantum Hamiltonian reduction, from invariant differential operators on V to differential operators on the invariants, differential operators on C of HW. All I'm saying here is that if you take an invariant differential operator, then it will actually act on an invariant function. And Wallach observed that in this way, that you can get a map, not only to get a map to invariant differential operators, but it's actually a surjective map. The image of phi is actually equal to invariant differential operators on H. So he proved this in some most of the cases. case by case, and Thierry Levasseur and I myself cleaned it up in the end. And there's some subtleties to this. First of all, the image of phi does not lie in d of hw. If I write the image of phi in terms of d of h, you'll find you get inverses turning up. And this goes, again, Harish-Chandra noticed this and showed that you have to twist phi appropriately to get an image inside d of hw. Once you've done that, then of course you have to show it's surjective. And this is important for two reasons. First of all, in terms of Harish-Chandra's work, it allows you to reduce questions about omega and g lambda to questions about d of hw, which, since you've got a finite group, are much easier to handle. And that in turn gives you extra useful ways, and he was able to use this to get important results about, for example, Springer theory. Okay, so that's quite a lot about one module, representation of G, and then one module or one class of modules over that, regular differential operators. So what about more general cases? So the next natural case to look at perhaps is the case of symmetric spaces. And here, various people have shown that Harish-Chandra's theorem holds. This is a particular work of Sekiguchi and Galina and Laurent, but it definitely doesn't always hold for the symmetric spaces. Tarassian, for example, has an example of an equivariant eigendistribution that's supported purely at the origin for a certain symmetric space. For Hotta and Kashiwara, there are no results. So what I'd like to do in this talk is to show how, if you like, explain what's really going on with these results. Why is it happening sometimes and not others? And how do they fit together? And also, what about the Hotta and Kashiwara result? So to do that, I better give you the definitions. So for a symmetric space, we take a second complex reductive algebraic group G tilde and assume it has an involution theta. So then we can take, this will split the Lie algebra of G tilde into the invariants, which is a sub-Lie algebra, and a vector space, the -1 eigenspace, which I'll call capital V. And then I've just got a corresponding Lie group, which I'm calling capital G. So here, the G tilde theta or G tilde G is called a symmetric pair, and V, the symmetric space I'm talking about, that's my V. And that is always a representation for both capital G and little g. These symmetric spaces are classified. It's a book of Helgason you can view, and there's quite a lot. There's a lot of them. There's 17 infinite families, for example. And important to notice that the adjoint action of G on V is a special case. Adjoint action of G on its Lie algebra is a special case, and that's just when you take G tilde to be two copies of G and theta swaps the terms. Then all the basic notation that I've introduced before goes through to this situation. The action of G on V induces an action on D of V. Differentiating that action, you get a map from the Lie algebra to the derivations on V. And crucially, the Chevalier theorem isomorphism still holds. The G invariant functions on V are isomorphic to W invariant functions on H, where H now is a certain subspace of V, which thought of as sitting inside G tilde is an abelian Lie algebra. And there's an associated little Weil group, associated complex reflection group, again, which I'll call W. So in this situation, the rest of the notation still goes through. We still have a discriminant, it's kind of defined in the same sort of way. And we have the Harish-Chandra modules G lambda. So remind you how they're defined. Just given a maximal ideal in sim VG, corresponding to lambda in H star, we take the left ideal of D of V, generated by the image of the Lie algebra, and this maximal ideal n lambda. Okay, so that's the situation we want to think about. So let's first of all start with an example just to solidify these ideas. And this is a case where one can take a fairly trivial example where we can compute everything by hand, but we still get some non-trivial consequences. So the situation will be, I will take the group G tilde to be SL2, conjugation by the obvious element, 1, 0, 0, -1. Then the group G will just be the torus, and V will be the matrices with zeros on the diagonal. So two-dimensional space. So its coordinate ring then, ring of functions, will be a polynomial ring in two variables, and I'll choose my variables x1 and x2 to have weights plus or minus 1 under the action of the torus. So then I'll write my ring of differential operators, the Weyl algebra. So that's polynomials in 2x's and 2 d by dx's. And the discriminant in this case, well, it just defines the two coordinate lines, so it's x1, x2. The image of the Lie algebra is just generated by the derivation x1 d1 minus x2 d2, and you can sort of guess that's what it must be, given it has weights plus or minus 1. And the invariance, CVG, that's just polynomials in the discriminant. Now that should be isomorphic to CHW. The way I'm writing it, you're not really seeing W or H, but it doesn't matter for us. And again, the symmetric algebra on V, if I take the G invariants, I'll get the analog to polynomials in Z. So this is polynomials in the element D delta 1, delta 2, partial 1, partial 2. So now we want to look at these G lambdas. In fact, I'll just look at the G0. So that's the module where I take my ring of differential operators and I factor out the left ideal generated by nabla, the derivation, and partial 1, partial 2. So I can describe completely the lattice of submodules, and it looks like this. So I'll describe it in terms of left ideals of D containing I. So remember, I is generated by the image of the Lie algebra and D1, D2, partial 1, partial 2. So then if I look at left ideals containing I, first of all, I can break this first term into 2. So I take x1 partial 1 plus x2 partial 2, and d partial 1 partial 2. And then I can successively remove the x's. So I can, for example, this J2, I'll remove the x1, J infinity, I'll remove x1, x2. And these are all the submodules. That takes a little more work, but it will follow, for example, from a theorem we'll give later. So these really are all the submodules. So if we look at the factors, first of all, the top factor, d mod J infinity, that's just the canonical way of writing the coordinate ring of V. That's just the canonical module for the ring of differential operators. And that appears again at the bottom. So if you think of J naught mod I, generated, for example, by x1 partial 1, that element is killed by partial 2. So there's because of this element. But also in the factor, x1 partial 1 is the same as x2 partial 2, and that's killed by partial 1. So again, this factor is going to be isomorphic to CV, isomorphic to the top. But if you look at the two middle terms, for example, J2 mod J0, that's now killed by x1 and partial 2. So that's torsion for the discriminant. So this example is good and bad. In the first case, we have Harish-Chandra's theorem that the only factor module is this delta torsion-free module. But again, there is some junk floating around, which is making it a little more complicated. So with that example in mind, we can see whether we can make a theorem out of that in general. So let's see the situation we've got. We've got our symmetric space V with G and little g as before, and we have the Chevalier isomorphism theorem. So once again, we have this quantum Hamiltonian reduction where invariant differential operators act on invariant functions. So that's giving us a map from D of Vg, invariant differential operators, to differential operators on the invariant functions. But now things become different because it's not true that the image of phi is actually invariant functions. Instead, what we have to do are use Cherednik algebras, as I mentioned right at the beginning. So associated to this H and W, you have a so-called Cherednik algebra. And what interests us is the spherical subalgebra of that algebra, which I'll call a spherical algebra. So I'm not going to define it in general. If you've seen the definition, it takes a while. Just think of it as being a deformation of my invariant differential operators corresponding to some parameter. And the crucial fact is it contains copies of both the invariant functions and the invariant symmetric functions on H. And the way to think about these is they look rather like primitive factorings of enveloping algebras, or certainly primitive factorings of U of SL2. And in particular, all the primitive infinite dimensional factorings of U of SL2 do appear among these A kappas. And given I've given you that definition, you can sort of guarantee what the theorem is going to be, is the image of phi is indeed isomorphic to one of these A kappas for some spherical algebra. And you could write down rather carefully what is that spherical algebra if you so desire. It's a bit of a mess to do that. And secondly, at least when the image is a simple algebra, then the kernel of phi are the obvious elements. So to think about this for a minute, if we're looking at the quantum Hamiltonian reduction says we're going to act on invariant functions. So in that case, certainly the image of my Lie algebra is going to act as 0. So the kernel of phi is going to contain the left ideal generated by d of g and then G invariance. And so the content of the second part is that's nothing else. Those are the only elements we find in the kernel. So I should comment, by the way, that this theorem is slightly deceptive in the way I've written it. I'm not using the simplicity of A kappa to prove this result. Rather, we know how to find all the simple algebras, and for each of those, we can determine what is the kernel. So the case when A kappa is simple, that's going to appear a number of times in this talk. So let me briefly discuss when we get a simple algebra. Oh, by the way, for the running example, my A kappa is indeed one of these factors of U of SL2, a simple factor. So when do we get a symmetric, simple algebra for my spherical subalgebra? Well, it includes 9 of the 17 infinite family of symmetric spaces in the classification in Helgeson's book. And I can be a little more precise. I still won't be precise in detail. So there are two cases that are possible. Either this parameter is an integer, or we have a nice symmetric space. Doesn't mean much, as I haven't told you what the parameter is, but let me just say that the case when kappa is an integer, those are the examples of that turn up in work of Beres, Ettingoff, and Ginsburg on rings of quasi-invariants, differential operators on quasi-invariants. And the nice symmetric spaces, this definition is a little more complicated, but basically it's those symmetric spaces which in their basic properties are closest to the adjoint case, where just G was 2 copies of the algebra. G tilde was 2 copies of G. So more formally, if you think about how you classify simple Lie algebras, one part of that is you define the root system and you get the corresponding weight space decomposition for G. And the key theorem you have there is that each of these weight spaces is one-dimensional. So in particular, you'd have this formula tautologically. And then we say that our symmetric space is nice. Well, you have this same basic root space decomposition, weight space decomposition corresponding to the restricted root system, and we demand that that same formula is true. So if that formula is true, we say that the symmetric space is nice. And that again is part of these 7 cases. So just think of this as, well, okay, there's a definition. These are the ones that are closest to the adjoint case, and there are these other ones coming from quasi-invariants. So with that notation in mind, we can say, well, what happens to our G lambda? So again, I'm going to assume always that A kappa, or almost always that A kappa is a simple algebra. And then I look at my Harish-Chandra module. Remember, that's the left ideal. I take D of V and I factor out the left ideal generated by the image of the Lie algebra and this maximal ideal from sim V G invariance. And the theorem simply states that it has no non-zero delta torsion factor module. So that's the Harish-Chandra theorem. But also we can get a somewhat stronger theorem that it has no delta torsion submodules. And that seems to be a somewhat harder theorem to prove. And remember here again, delta is the discriminant in this setup. By the way, if A kappa is not simple, then this G0 always has a non-zero delta torsion factor module. So the theorem just doesn't hold if A kappa is not simple. So this, if we just think about what that means in terms of the earlier discussion. So first of all, you could say that G lambda is the minimal extension of its restriction to the regular locus. That's when delta is non-zero. And that this L, this restriction, is a nice object, is an integral connection. And secondly, if we were thinking about G-equivariant eigendistributions on the appropriate real form of V minus phi0. So if we tried taking an equivariant eigendistribution supported on V minus phi0, then it would have to be 0. So if you like, this generalizes Harish-Chandra's theorem 1 quite nicely. And for the nice symmetric spaces, this part 1 was conjectured by Sekiguchi. And for the part concerning eigendistributions, that was proved both by him and by Galina and Laurent. So they proved that there was no delta torsion factor module. And that in particular proves part 2 of the corollary. So I think that generalizes that theorem quite nicely. And it also sort of explains the comment I made earlier about, how does the Sekiguchi and Galina, Laurent were showing that in certain cases, you were able to get this corollary, this consequence, this generalization of Harish-Chandra's theorem. But there were these other examples of Torossian where you had G0 equivariant eigendistributions supported at the origin. And in his example, that would be something fitting into case 2. And in fact, it would be a situation where the A kappa had a finite dimension, a one-dimensional simple module. So that's sort of seeing that the structure of the Cherednik algebra really is influential in the structure of these distributions. So that's describing the Harish-Chandra theorem. What about the Hotta Kashiwara theorem? So remember, that was the theorem that said, if this G lambda, in the adjoint case when V was G, this G lambda should be semi-simple. But if you remember back with the running example, we showed there that the module was not semi-simple. It had this delta torsion-free top and bottom, but sitting in the middle was a load of torsion junk. So that means we're going to have to be a little more subtle in how when we work out when G lambda is semi-simple. And to do that, we need to think about the Hecker algebra. So again, this is an algebra I'm not going to define. Many of you will have seen it. So associated to my basic data, we have this deformation of the group ring CW. And just as the Weil group W is intimately connected to the representation of G, so the Hecker algebra is intimately related to the representation theory of A kappa. So it's not surprising it should appear in this sort of question. And again, the theorem is then easy to state. This is the theorem with Bellamy and Nevins. Suppose I have a symmetric space. Then the G0, let's just think about G0. So G0 is actually semi-simple precisely when the Hecker algebra itself is a semi-simple algebra. And I don't need to worry about whether A kappa is simple in this situation, because if the Hecker algebra is semi-simple, it turns out so is the ring A kappa. And if I look at the running example, so in that situation, the G tilde, remember, was SL2. G was just the torus. The Weil group was just a group of 2 elements. And this theorem failed there, so the Hecker algebra could not possibly be semi-simple. Well, what's the only possible non-semi-simple deformation of the group of CW, W being 2 elements? And that's the polynomial ring T mod T squared. And that indeed is what is the Hecker algebra in that situation. I've only stated the theorem for the G zeros. I can there is a similar result for all the other G lambdas, but I'm not going to state it because it just requires me to bring in a load more notation. I've got enough notation already. So then, as I said before, when I was talking about the Hotta-Kashiwara theorem, you can specify what are the irreducible representations. And so we have an analogous sort of theorem here. So let's suppose we're in the situation where H kappa is semi-simple, so A kappa is simple. Then G0 breaks up into a direct sum of simple modules, G0 rho, indexed by irreducible representations of the Hecker algebra. And each of those appears a dimension of rho times. And if you package them together like this, you can even think of it as a bimodule over dv and H kappa. So that gives you quite satisfactory analog of the Hotta-Kashiwara theorem. But of course, you may complain here that I've not really answered the question. I've just replaced the question I'm interested in by a different question. To complete this theorem, I should really tell you exactly when this Hecker algebra is semi-simple. Unfortunately, lots are known about Hecker algebras, and so I can tell you in considerable detail, in precise detail, when this Hecker algebra is semi-simple. So that gives us the following theorem. So I'm just stating for simple algebras, I can take direct sums of these to get the general case. So given our symmetric space V, assuming that the algebra is simple, then the Harish-Chandra module G0, that is semi-simple in precisely the following cases. First of all, we've got the adjoint case. That's the Hotta-Kashiwara case. Then we have three other cases. We could take G tilde to be SL2n, inside which G would be an SP2n. Or I could take SO2p, and inside there I'm going to take SO2p minus 1. And then there's one exceptional case where I have F4 sitting inside G6. And you can probably, if you fiddle away in the bar tonight, work out what is the involution that corresponds to this. By the way, in terms of this notation, if we take the running example where I started off with an SL2, that is again part of an infinite family, but that would be the infinite family where I have SL2n and then an SO2n sitting inside. SLN, SON. Okay, so this is a bit embarrassing. So back when Lavoisier and I were first thinking about this, generalizing the Hotta-Kashiwara result, we actually conjectured that G0 was semi-simple for all possible nice symmetric spaces. We're only thinking about the nice case in those days. So what about these other three examples? Well, that first one's not nice. It's not a nice symmetric space, nor is the second one, nor is the third one. So in other words, we've made the worst possible conjecture where it's completely false everywhere except for the case that was already known. So it's undoubtedly our worst possible conjecture. It's actually probably one of our better conjectures because it meant that we kept thinking about the problem and eventually led to this present work. So that gives us these generalizations, both of the Hotta-Kashiwara result and of the Harish-Chandra result. So, as I said in the beginning, one of the ways we should really be thinking about this is the interrelationship between modules over the ring of differential operators, which are G-invariant, and modules over the Cherednik algebra or its spherical subalgebra A kappa. And the way we want to interrelate those is to think about certain categories of modules, highest weight modules. So for U of G, you have category O, the category of highest weight modules. We have natural analogues of both of those for both A kappa and for D of V. So for A kappa, this is known as the spherical modules, O spherical. So these are the finitely generated left A kappa modules on which sim HW acts locally finitely. Remember that A kappa looks a bit like a factoring of U of SL2, so it contains inside it copies of sim HW and C of HW. And you do the same thing with D of V. Here now you look at G-equivariant left D of V modules, but again, this sim HW, thought of as sim VG, should act locally finitely. And just by its definition, this will contain the G lambdas. And the G lambda the generator 1 there is killed by mu of G, so that gives us the G-equivariance, and by the appropriate maximal ideal of sim Vg. And the way we want to prove the previous results, and the way in which we relate these two things, is that we think about this bimodule where we take d of v and we factor out the image of the Lie algebra. So one of the first theorems I stated was talking about what was the image of, what was the quantum Hamiltonian reduction and what was the kernel of that map. And that can just be condensed into the statement that A kappa is nothing more than the G invariance of M. And again, we can rewrite our Harish-Chandra module, G lambda, by saying we're going to take this module here, and under the right action of A kappa, we tensor with A kappa mod A kappa times M lambda. And maybe I'll give two generalizations of the results we had earlier into this context. So first of all, remember we had the earlier theorem that not only did G lambda have no delta torsion factor module, but it also had no delta torsion submodule. And that can be generalized into the following result, which says that if we take a non-zero submodule of G lambda, then first of all, its G invariance is a non-zero. That, by the way, you can also identify with the holomorphisms from M to L. And that is, by the way, always going to be a module in O spherical. That's not surprising, because if L has a finite action of, locally finite action of C of H, or sim HW, the same is going to be true of invariance. And this really does generalize that earlier result, because if L happened to be a delta torsion submodule of G lambda, then that would still be true of LG, and that you can easily prove is not possible inside O spherical. So this generalizes that result. So this gives you a nice way of, if you've got modules over the, or G-equivariant modules over D, you can get yourself modules over the spherical algebra. Going the other direction, I'm going to state the following result, that if we look inside the admissible modules at our module G lambda, it's particularly nice. It's a both projective and injective object. And phrasing things this way, we should say, well, what about other modules starting from A kappa? And in fact, everything we've been stating so far, I could generalize, rather than looking purely at G kappa modules like this, I could start with any projective object in O spherical, and then tensor up with M to get myself a D module. And then everything, both these theorems and the earlier theorems, hold in that generalization. So I think that gives you a hint of how we can interrelate results over D of V and the spherical algebra A kappa. So there's a number of other ways we can generalize these results. First of all, you could say, well, what are you really using about spherical algebras, symmetric spaces, I mean? And the real thing we're using there is that we have this analog of the Chevalier isomorphism. And that works more generally. Probably the most general class of representations for which you have such a Chevalier isomorphism are the polar representations of Dadok and Katz. And these contain a lot of other interesting representations. And I won't give the definition of that, but I'll just give one example. So suppose, as in Damien's talk, we take a quiver. Let's take the cyclic quiver in this case with L nodes. And then I'm going to take the representation space where the dimension vector is just a constant n for some n. And then I'm going to regard that as a representation for the product of L copies of GLN. So I might remark that if I go back to my running example, that could be regarded as V21, the quiver of two nodes and dimension vector 1, 1. So in that situation, you argue, well, I should be having GL2, and actually I had an SL2, but the extra central element of G acts trivially, so there's no real difference. So in that situation, all our earlier results apply to these VLNs. So the first result, That was result 5, which was saying that we understand both the kernel and the image of quantum Hamiltonian reduction. The image should be a spherical algebra. That's actually an old result of Oblomkov and Gordon. But as far as we're concerned, all our early results about the modules, the G lambdas, apply in this situation. And I just want to mention what happens for the module G0. And here it's really quite striking. So remember, if I looked at V21, there my module had length 4, simple top, simple bottom, both of which are delta torsion free, and there's some delta torsion junk in the middle. And when I look at the VL1, so now I have L nodes, but still dimension vector 1, 1, 1, 1, it still has a simple top, still has a simple socle, but now in the middle, you'll have 2 to the L minus 1 delta torsion factors, subfactors. So I really don't understand what's going on here. I mean, I understand why the theorem is true, and I can prove it, obviously, but quite why it is that these modules should have this striking structure, that the thing you're really interested in, being the socle or the image, or its top or its bottom, those are nice delta torsion modules, and so you can actually get some strong consequences from that. But then you have this mysterious torsion junk sitting in the middle. I really don't understand how that goes. So to finish off, let me just give you a very brief idea of how the theorem, I should say, all the early results we've given work at the level of polar representations, but the results are not as clean. You have to add extra conditions. And that's why I've only ever stated things for symmetric spaces. So let me finish by giving you a brief idea of how the proof works. So to condense my notation, A will be A kappa, D of V, and then M was this bimodule between the two. Then for the Weil algebra, we have the Auslander duality, taking X at the top dimension to D, gives you duality between left and right holonomic modules. So here my N plus M will be the global dimension of D of V, or half the GK dimension of V. And due to results of Losev, because I'm assuming A is simple, you have similar results for this spherical subalgebra. So basic facts about this is this D of V, this D gives us duality between left and right holonomic modules, and it acts nicely on admissible and torsion. So it maps admissible modules to admissible modules, torsion modules to torsion modules. And the same is true for duality DA. And the other fact I want to mention is that down with O spherical, this torsion business is easier to understand. As soon as something's an O spherical, it has the minimum possible GK dimension. If then I tried factoring out a power of delta, I'd have to drop the GK dimension further, and that's not possible. So this Z cannot have delta torsion. And again, I'm thinking there of delta as lying inside A. So with that notation, we have an intertwining theorem, which says if I suppose I want to take the dual of my G lambda, well, break it up, it's M tensor N lambda, then I can take the dual of N lambda, and I tensor up. Well, I have to tensor up now with a appropriate dual of M to get them, because this is now a right module, not a left module of A. So now I want to take the theorem we were talking about, at least when A kappa is simple, this G lambda has no delta torsion. So let's look at that part of the theorem. So suppose not, suppose it has a torsion submodule. So I can take this dual, and that'll give me a delta torsion factor module of the dual of T. And that lies again in my admissible modules, the right modules, not left. So tautologically, that just says I've got a non-zero homomorphism from the dual of G lambda to S. And again, I break that up, that G lambda up as M tensor N lambda. And then I apply this intertwining theorem. I break that up further to the dual of N lambda tensor M prime. Remember, M prime was an appropriate dual of M. So about the only thing I can get from that statement is that this, then I should apply a junction. So then I break up this tensor product to D of A m and then homomorphisms from m prime to s, and then I take A homomorphisms. So about the only thing I can take from this expression is that that last term is non-zero. So what do we know about this last term? Well, it may not be finite. It's an A module, but it may not be finitely generated, but that's not a big deal. Take any finitely generated A submodule. Then, as I said before, for DD, and the same holds for DA, torsion and such like behaves well under duality. So this submodule of Z prime of Z will lie in O spherical, on the opposite side, and it will also be delta torsion. But the second theorem I sneaked past you was that those things aren't allowed. This submodule Z prime would have to be zero, in other words, Z zero. So therefore T zero. And I have no delta torsion factor module. So that gives you a hint as to how the proof works. So it's very much interplay between modules over D of V and A kappa. And the same is true for the other results. So at that point, I'd like to thank you very much for your attention and happy birthday to Michelle. Thank you very much.